Okay, in this video, we're gonna run a constant head hydraulic conductivity or permeability test on sample A. And the equation for the constant head test, you can easily derive it from Darcy's law and just kind of go from there. That's what we've done here. This is, the equation comes down to the flow volume times the length of the sample divided by the time it takes to measure this flow volume times the head, the change in head across the sample, and the cross-sectional area of the sample. So that's kind of all laid out right here. So for this test, this is the data sheet. The sample length. Okay, if you have a look down here at the sample, there's a little ruler right here, and it shows kind of the height of the sample. It looks like 7 centimeters. So that's the sample height. The diameter, it's also on the data sheet, but it's here, so that's 10.16 centimeters. So you can calculate the cross-sectional area. And the dry mass, or the mass of the solids that were put in here, we have 721 grams of material. So with the diameter and the height, you can calculate the volume. You have the mass of the solids, so you can calculate dry unit weights, and you can calculate void ratios with a specific gravity that's on the data sheet, 2.66. Okay, so in the last video, when we kind of showed you how the Marriott bottle worked, we showed that for the constant head setup, when we had the valve closed up here and we had the water level above the bottom of the bubble tube, that the head across the sample was this vertical distance between the bottom of the bubble tube and the outflow. And per the datum, i.e. the ruler that we have on the side of the Marriott bottle, it's equal to 30 minus 23.2. So I just wrote it like this because I think it's more clear as to where the number comes from. So I think that's more helpful. So what we're going to do, we're going to use this, we're going to do a couple of trials. We're going to catch some flow volume over some time. We already know the head across the sample. We just talked about the length. You can calculate the area. And so with the equation, you can calculate K for that given flow rate or flow, and that flow volume, and the time it takes to acquire that volume. So we're going to do 2 trials, and you're going to do the normalization to K20, so we'll take the temperature as well, and you guys can, as you're watching this video, fill out the data sheet and all the values, and you're going to use those for your report. So we're going to unstopper this. I got bubbles coming in, so I'm going to start the timer. Okay, I'm going to start the timer and start catching the flow. We're going to do 2 trials. They'll be about a minute-ish each. So we'll do a minute. So 1 minute. So the time was 1 minute. We got 365 for the flow, so 365 milliliters or 365 cubic centimeters. We'll do it again. So your 365 is your capital Q, or your flow volume, for the first trial, and that was in 60 seconds. just go to a minute again on this one. All right, in a minute, second trial. 360, we'll call it 365 again. So same thing. All right, that's good. Nice and repeatable, like that. And now we'll take the temperature. And that looks like 18 degrees, so that's your temperature for your normalization. So you can now, based on, you have the time, you have the flow, we did, the trials were the same. Yeah, and so you can calculate your K value and normalize it to 20 degrees. And then another video, we'll do the falling head test.